Okay. All right. So now that's if we allow repetition. But what if it turns out, let's see. What if somehow we don't allow repetition? So this is question 2. What if we did not allow repetition for some reason? The bank has a new rule that no, you can't repeat digits. Well, in that case, what's going to happen? Let me write down here. It's still a 5-digit password, right? Well, you have 5 choices for the first digit, right? You have any of those possibilities, okay? But whatever you pick here, you can't use again. So if I pick, let's say, number 1 here as my first digit, right? So we're making that 5-digit pin. If I chose 1 as the first digit, I can't use 1 again, can I? So how many choices do I have for the second? I can't see the chat, so just say it out loud, please.
4.
Thank you. 4. I love the enthusiasm. I really do, actually. But we have 4 choices. Oh, I'm an idiot because it's right there. That's why. Okay, that's recorded. So we have 3, 2, and 1. Right. So we have 1 less choice each time. So I used 1, so I can't use it again. Say if I use, I don't know, 3 here, I can't use that again. So now 2 choices are gone. So we have this now by the counting principle, as you can see. Okay. So basically what I'm trying to illustrate to you is this new concept of a factorial. Here. So what we have is 5 times 4 times 3 times 2 times 1, which is 120 possible passes now. A lot smaller than this. This kind of product where you're decreasing by 1 each time, that's actually very useful. It's what we call a factorial. So for any positive integer n, okay, n factorial, it's denoted by this. They have an exclamation point here, right? This is by definition n times n minus 1 times n minus 2, and so on and so forth. You're decreasing by 1 each time until you get down to 1, and you multiply all those together. And I did some calculations here. For 1, if n is 1, 1 factorial, well, you just get 1. I mean, basically, if n is 1, okay, then you only have 1 there. So you can think of that as part of the definition. 2, you have 2 times 1, which is 2. So 2 factorial is 2. 3 factorial, that's 3 times 2 times 1, which is 6. You have 4 factorial, okay? And that's 4 times 3 times 2 times 1, which is 24. And, you can keep on going. And this might throw you off a bit, but people, what they also do is we define 0 factorial to be 1. It's really more of a convention, I guess like part of the definition if you want. And what's nice about that is what we can then write is this. N factorial is the same as n times n minus 1 factorial. I mean, essentially, you could just, if you replace n here by n minus 1, you would see what n minus 1 factorial is. So this equation should make sense. It's almost like if I threw this n away And what's on the left over here, this whole product here is the same as n minus 1 factorial. That's all. All right, so we have that here. So if we go back to our password example, okay, we have those factorials. So let's kick this up a notch, so to say. We're going to make these passwords again, okay? Again, we're not going to allow repetition, okay? So we're making a 5-digit password, okay? We can use any one of these 10 digits now, okay? We have 10 digits here, okay? Now, how many 5-digit passwords can we make if repetition is not allowed, though? So it's similar to what's before, though. We're making a 5-digit password, but we have more choices. So it's the same idea. We have 10 choices for the first digit, okay? There are 10 digits here. We're not allowing repetition, so whatever we choose there, we can't use again. So there's only 9 choices here. Okay? There's only 9 choices here. And again, you know, after the second one, after the first 2 are chosen, those 2 cannot be used again. So we're down by 1. We're down to 8. Keep doing this for the first 5. We get this product. That's where this product is coming from. But this is the same as 10 factorial, okay? But you're dividing by 5 factorial. Yeah, I didn't write it out here, but you can write it out on your own. It's really not hard to see that this product is equal to this quotient. That's really what I'm trying to get at here. And again, with passwords, the order does matter. So essentially here we have a situation where order matters, okay? And repetition was not allowed. That actually leads us to this slide, which is permutation. Okay? So basically we have a situation where, okay, where order matters, but repetition is not allowed. In other words, we have without replacement, as most people would say. So repetition's not allowed, and it's without replacement. That is, without replacement, excuse me, and the order of selection does matter, okay? Well, then, if you have n possibilities, right, you're arranging r of them, okay? Now, like in the previous example, we had 10 possibilities. We were arranging 5 of them. The total number of possible arrangements turns out to be this. The book actually gives you this formula, then comes up with this one. I figured it'd be good to give them both at the same time. It's really similar to what I did on the previous slide. Namely, you have n factorial, you can write them out, and then, you know, it's the same thing as just dividing. So hopefully it's not too, I hope it's not too hard to see. So, and this formula here is kind of, it's not terrible, but I personally would use the factorial symbol. The factorial notation's here. It's a little bit easier. In fact, when you have ordered arrangements with no repetition, you have permutation. So those passwords were actually here. These passwords were actually permutations. They were 5 digits long, and each password, for each digit, there were 10 choices. So we were arranging 5 of the 10 digits here. And each choice gave us a permutation. Basically here we had n was 10 and r is 5. And now I don't know what kind of calculator you have, if any, but I know in Desmos at least, and there's other places do this as well, other calculators, they have notation that looks something like this. or what's in the book. The book's notation is a little bit different. That one looks something like this, except I couldn't get the subscripts written though, so that's why I'm sticking with this notation. So P of NR is the permutations, excuse me, the number of permutations from N possibilities, and you're arranging R of them. So N is how many possibilities there are, and you're arranging R of those N possibilities. Okay? So you have N choices, in other words, and you're arranging R of them. Each permutation is size R. Again, it's slightly different than what's in the book, though. But the main thing is that replacement, order matters, okay? So if you change the order, you get a different thing. That's when permutations come into play. Let me just, hold on, let me pause